Greetings ladies and gentlemen, I'm Irento Jaya from NTU, together with Professor Chai Wentong from NTU and Associate Professor Lee Yisen from Nankai University, we wrote a paper titled Rendering Server Allocation for MMORPG Players in Cloud Gaming. Before we start, I want to get through the agenda for this presentation. First of all, I will describe the background of this paper, followed by the problem definition. Secondly, I will show our proposed solutions with all our assumptions in this paper. After that, I will describe the experiments that we have conducted and the results out of them. Finally, I will close the presentation with our conclusions and future work directions. There are two key ideas that motivate our study. The first one is multiplayer cloud gaming. In contrast to existing single-player cloud gaming, there are a lot of existing single-player cloud gaming services in which the game runs in the cloud, and if multiple players are playing the games in the same server, the games just runs different instances of those games. And in single-player cloud gaming, each player is independent from each other. So on the other hand, in multiplayer cloud gaming, players coexist in the same virtual space such that they can interact with each other and they can see common objects in the virtual space. Furthermore, from the cloud gaming service provider's point of view, running servers costs money. Therefore, in this paper, we formulate the problem and propose some possible solutions for cost minimization. To give a clear image of our paper, here is the executive summary of it. The problem we are tackling in this paper is an allocation problem in cloud gaming between players and rendering servers, or RSs, where the rendering occurs, with the objective of minimizing the cost of using RSs. From the experiments, we observed that RS resource capacity is the most limiting factor in the allocation compared to latency constraint. Therefore, we make use of rendering workload sharing in order to ease the burden on RSs. And finally, we will show how much the workload sharing reduces the overall cost. Moving on, I would like to mention what existing works have studied in related fields. There are 4 subtopics in our related works. We are cloud gaming, QoE, resource allocation, and multifield rendering. With cloud gaming, the concept is to move the game assets and logics out of the player's devices to remote servers such that the game itself works as a black box where the rendering process takes place in RSs. Each player sends game input and receives video stream as feedback. Hence, playing the game is not much different from interacting with a video player. I will explain the system architecture of cloud gaming in the next few slides. Furthermore, as the game interaction occurs between 2 nodes, latency and bandwidth limitations are unavoidable. The quality of experience, or QoE, is the gameplay quality perceived by the player, such as video quality and responsiveness. There are existing works which minimizes the latency by allocating the players to appropriate RSs, or how to get the optimum video quality for the players. This issue brings us to the third subtopic, which is resource allocation. In this case, the resource allocation are allocations between players and RSs, which has been proven to be NP-hard. Moreover, in this paper, we formulate the problem over multiple time instances in an online setting, which future requests are not known at present time. On the other hand, offline setting assumes all events and occurrences are known at its time instance. Finally, we also consider multifield rendering as one of workload sharing technique that an object can go through part of a rendering pipeline once for rendering for multiple viewers. This technique has been used in VR application, which renders an object once for both eye viewports. The diagram on the left-hand side shows rendering pipeline without multifield rendering, while the diagram on the right-hand side shows rendering pipeline with multifield rendering. With multifield rendering, the rendering process is divided into 2 parts: view independent, which is independent from the viewer's perspective, such as point cloud rendering, while view dependent depends on the viewer's perspective, such as light projection. Therefore, an object which is seen by multiple viewers can go through few independent rendering once for all viewers before it goes through few dependent rendering for each viewer. Few independent rendering takes place in CPU, while few dependent rendering is performed in the GPU. In the diagram, the red and the blue rectangles represent the rendering process for two viewers. With multifield rendering, the few dependent rendering process for the blue viewer in the GPU is derived from the few independent rendering of the red viewer in the CPU. Summarizing the existing works, there are still a few problem areas which are not extensively studied. Some of which covered by our paper include multifield rendering in cloud gaming by using dependency between players allocated to one RS because we are considering multiplayer games. And finally, the optimization offer multiple time instances in contrast to existing one-shot allocation for a single time instance. Before I start with the problem formulation, I want to show the architecture design of cloud gaming. This is the conventional or well-known cloud gaming architecture. As we can see from the figure, the clients only perform I/O operations while all the game logic and the game scene rendering occurs in the remote cloud. Each client is represented by a virtual machine or VM session in the rendering server. In this paper, we propose a new cloud gaming architecture to tackle those existing problems. In order to make use of workload sharing, especially from the common objects seen by players in the same virtual map, the rendering process is split into map-level few independent rendering and player-level few dependent rendering. Furthermore, we also split the game server into a central game server to maintain non-visual information such as the game database and login information, while the map servers maintain the game scenes. This is the cloud gaming architecture that we propose. As we can see in the RS, there are two rendering stages. The first stage is in the map level, performing few independent rendering for all players in the virtual map, because they can see the common objects in those maps. Then few dependent rendering is performed for each players, and in our architecture they reside in the virtual machine. They result in 2D projections packaged as video streams. After we settle with our architecture, we formulate our problem as a cost minimization problem. The cost comes from the RS rental cost, since RSs come from third-party service providers such as Amazon EC2 and Microsoft Azure. There are two constraints to be satisfied. Server capacity constraint, because those servers have limited capacity, and latency constraint, because we have different nodes interacting with each other, as we have seen before. The workload sharing from multifield rendering affects the server capacity constraint, as more players can be served by a single RS. Therefore, our hypothesis is that workload sharing reduces the number of required RSs and hence reduces the overall cost, which helps to achieve the objective. To put in mathematical terms, this is the variable that we are using in our mathematical representation. The objective is cost minimization here, and the cost of each RS only counts if the RS is serving at least one player, as represented by the variable z here. Here we have one implicit assignment constraint, which a player can only be assigned to one RS. The RS capacity constraint consists of CPU and GPU resource capacity constraints. The CPU workload consists of few dependent rendering for each player and few independent rendering for each map. On the other hand, GPU workload only consists of few dependent rendering. Finally, latency constraint is to make sure that the responsiveness perceived by the players achieve a certain QoE standard. The latency is defined as the latency between a player with the RS plus the latency between the RS and the map server. This problem formulation comes with several challenges. First of all, there are trade-offs that we have to take into account when we do the optimization, such as between capacity and latency constraints. Which one should we satisfy first? Which one should we put as our priority? Secondly, as resource allocation has been proven by existing studies to be NP-hard, online allocation for multiple time instances is also NP-hard and is harder to solve. Moreover, it is not possible to derive a simple algorithm out of the problem formulation described in the previous slide. Therefore, we come up with 4 online heuristics to do the allocation. All of these heuristics will search for eligible RSs from the list of active RSs which are currently serving one or more player. If no such RS is found, the search space expands to inactive RSs to be activated. The first heuristic, lowest price or LP, is a very simple heuristic which only looks for the cheapest RS. Secondly, lowest waste resource or LWR aims to be the best fit algorithm by choosing an RS with the lowest waste or unused resource. The waste resource is calculated using the total capacity subtracted by the current RS workload. The type of resource used in the calculation is the more demanding one, whether the map is CPU or GPU intensive. Then, highest workload share or HWS is an extension to LP by filtering RSs with possible workload sharing before performing LP. Finally, lowest waste price or LWP is very similar to LWR, but it takes into account the rental price of each RS. In order to evaluate the performances of these heuristics, we come up with 2 offline algorithms, local search or LS and lower bound or LB. LB is an optimal solution derived using a mathematical solver. LS aims to empty RSs with low utilization. As how local search is generally implemented, we start at getting the first solution. So for example, we start at this point in the curve. Then we try to reduce the cost by moving along the curve until we hit a local minimum in which we cannot decrease the cost any further. So if we start here, then we will end at point A. If we start here, then we go down all the way until we reach point B. By using local search algorithm, we will arrive at a local minimum instead of a global minimum, because we will never know we don't know whether a local minimum is a global minimum because we stopped the search there. So in our paper, the LS solves the allocation to get the first solution. We use a very simple algorithm. So in this case, we are using LP, the lowest price. And then RSs are sorted with increasing number of players spanning across multiple time instances. We know this information because LS is an offline algorithm, so we know the player allocation for all time instances. LS then attempt to move each player from an RS to another RS with higher index until there is no possible move. This moving attempt is how we move along the curve, and we stop when there is no possible move because we already reached the local minimum at this point. And in this paper, we use LS as an approximation of the lower bound of the online heuristics. Moving on, here is our experiment setups and some assumptions we made. We use more than 500 Planet Lab nodes to simulate the players. Map servers and rendering servers are hosted using Amazon EC2 and Microsoft Azure. All players and servers are located in the Americas. Player arrival and playing duration follows Poisson and exponential distribution, respectively. Then we assume that we have fixed number of servers, maps, and players. The latency between nodes never changes, and there is no rejection for each incoming player. So each player will be allocated to an RS and exactly one RS. Here is the more detailed experiment parameters. The number were taken from existing MMORPGs such as Final Fantasy XIV and World of Warcraft, and the number were scaled down to match our simulated environment. This is our experiment results using the heuristics over increasing player arrival distribution parameters, which indirectly translate to arrival frequency. This experiment was conducted to observe the scalability of our online heuristics. And as we can observe from the figure, LWP has the lowest cost compared to other heuristics because it takes into account 3 factors at once during the decision process, which are the workload reuse, RS capacity, and RS cost. And also, the online heuristics do not scale the cost linearly compared to LS because the y-axis here is the rental cost relative to LS. This shows the limitation of the online approach compared to its offline counterpart. So here we know that our online heuristics that do not scale as well as LS, at least. This figure shows our experiment with 24 unique parameter settings to see the impact of each parameter on the cost. There are 4 parameters involved in these experiments. For RS pricing, we experimented with both uniform pricing, where all RS cost equally, and variable pricing, which we use the actual cost from the providers. Then on the second row here, we have dominant resource. C means CPU intensive, and G means GPU intensive. It means whether the map is more CPU or GPU resource demanding to render. The later H here means hybrid, which is a mix of CPU and GPU intensive maps. We also experimented with relaxed and strict latency constraints. And finally, we set the few independent workload ratio into 2 levels, high and low, to observe the impact of workload sharing. So as we can observe from the figure, LWP has the lowest cost in most cases. However, its gap with LS is much more significant than other heuristics, as it has been shown in the previous figure as well. Since we have more GPU resource than CPU resource in the rendering servers, in GPU intensive setting, which is P5 to P8 and P17 to P20, compared to P1 to P4 and P13 to P16, the cost of GPU intensive setting is lower because we can fit more players into the same amount of rendering servers. We can also see that the number of even number P, here P2, P4, P6, and until P24 has lower cost compared to its previous P, which is P1, P3, P5, up until P23. This shows the benefit of workload sharing because the few independent workload ratio here is higher. This brings us into the next figure. By comparing the cost with and without workload sharing, we can confirm our hypothesis earlier to be correct. Our experiments show that workload sharing reduces the cost in all cases. Although cost reduction from workload sharing is not that significant in LS, it is beneficial for online setting. Because in real life, it is online setting. We don't know what will happen in the future, so we can only rely on online setting. And this is and workload sharing is beneficial in online setting. Finally, here is the comparison of the performance between show offline algorithms. As we can observe, even LS has a significant gap above LB that grows together with player arrival distribution parameter. As LS only considers one direction of minimization, which is one direction of moving along the curve compared to LB, the difference of the performance of the minimization becomes more visible when more minimization directions are possible with higher player volume. To conclude our paper, we have proposed an MMORPG cloud gaming architecture supporting multifield rendering to allow workload reuse, which results in reduced RS rental cost. Moreover, the online heuristics does not scale with the cost as good as offline algorithms. For our future works, there are some directions we are interesting to look into, which includes player request rejections, where there is no eligible RS to serve an incoming player, involvement of edge servers for stricter latency requirement games, and using machine learning to predict the future requests so that online allocation can be more cost effective. Thank you for your attention. We are now open for question and answer session.